Hello everyone and welcome to this Pico Academy introduction to NVH. The idea of this presentation is really to give you we're trying to simplify an overview on NVH. It's quite a complex subject, so we'll do the best that we can. My name's John Parker, I'm Distribution Sales Manager. I'm joined today by
Steve Smith, Automotive Application Specialist here at Pico.
So we're going to be running through NVH, the theory, and also doing some practical stuff on vehicles. So without further ado, let's get on with the presentation.
Let's go.
Okay, so let's get straight on with the presentation on NVH. So we're going to be looking at these main subjects. First of all, we're just going to go through what is NVH, so noise, vibration and harshness. Then we're going to have a quick look at connecting to the vehicle. So basic connections at the first instance. Then we're going to have a run through the NVH kits and vital accessories that you're going to need to start to understand where and when you would use them. Then we're going to just have a look at how you download the software and how we make that operational. And then we're going to start to do some practical tests on vehicle. And finally, Steve will finish off giving us some example case studies of exactly where NVH will be really valuable for you and your workshop. So let's continue. What is NVH? Well, as I said earlier, it's noise, vibration and harshness testing. So there are three things that you've got to start to think about when we're talking about NVH. First being noise. So that is defined as an unpleasant or unexpected sound in the wrong place at the wrong time. Then we have vibration, and that is defined as an objectionable, repetitive motion, either an up or down, a back or a forth movement that you can feel. And then finally, and possibly the harder one to try and understand, is harshness, and we define this as an aggressive move and a single input. So we'll have a quick look at this in a little more detail. So we'll just run the animation. So we've got our little man here who's picking up, quite happy to begin with. We've just got music in the vehicle, but what do we see as noise, vibration and harshness issues? Here's a noise that moves into a rattle. So this is our noise turning into a vibration. So of course he's unhappy in that environment. And then we're going to have a quick look in this case. So we've run over a pothole, and that's something that we would describe as harshness. And these are all feelings that you will see as you're driving a vehicle. So we take most of our data from, and most of the issues you will see in the workshop will come from the driver generally, or other passengers feeling something within the vehicle, and it's by understanding their feelings and obviously noises that they pick up, we need to then to look into where the problem is. So that is very simply NVH. Okay, so we're going to have a look now at the theory of NVH, and there's a lot to take in, and we are going to do it because we've got limited time with this video, but there is a whole range of videos we can go back and find out more information here. But we're just going to take you through a few slides here on the theory of NVH and the way that we as humans perceive different levels of sound in different ways, measuring in hertz between 0 and 20,000 hertz. So I'm just going to play the animation, and Steve's going to talk us through this actually.
Yeah, thank you, John. So 0 to 20 hertz, that's vibration only. So that's where you need to be looking in the spectrum for complaints of vibration. 20 to 200 hertz, that's a combination of the two. We're both different. We may perceive as a vibration or a noise or both. And then from 200 hertz onwards to 20 kilohertz, 20,000 hertz, that is noise only. So that's, there's that awful brake squeal. That's where we're using the microphone to capture those frequencies.
And then once we've got a head around the kind of noises and vibration we feel, we need to really start to understand about the different places within the vehicle, within the machine that we're operating on, and how they affect each other. And then we call these, first of all, the source components. That tends to be the cause of the noise or vibration. And then we have something that we call a transfer path, which again results us towards a responding component. So you have to understand that where we feel the issue, perhaps in the cabin, isn't necessarily, so the responding component is perhaps the steering wheel where we're holding on to, but it isn't necessarily the source of the issue. And Steve will always give this really good example. We've got a problem with tyre or in the suspension, but actually it's causing a rattle on the dashboard. Which should we fix? Should we fix the source component, or do we just kind of pack out the dashboard to try and solve the problem? And that's a really good way to think about it. So it's a really useful thing to start to get your head around, having this idea of a source component, the transfer path, which will be through the mechanics on the vehicle, and then of course the responding component, which is how your customer feels the issue, and about which item you rectify. And once again, we've got a short animation on this, and I'm going to let Steve, if he doesn't mind, just to talk us through that one.
Okay, so here is that theory in practice. So imagine here we have an unbalanced road wheel. So we have that tendency for that wheel to be moving outward as the weight reaches the top. There is our imbalance. And ultimately that's going to manifest itself and transfer through the suspension. So we see the vibration there. And look how that energy is dissipating through the vehicle and ultimately up the steering column, which acts like an antenna where we are connected to, and we feel that vibration. There's our responding component. Now, of course, we could try and doctor the steering wheel some way, but that's not the procedure. We would be looking at going to the source in this scenario and balancing out the road wheel.
Great. So then we have to start to think about vibration orders, and we push these to 3 different types. We abbreviate these. So we have E, but that is essentially engine, so engine order vibrations. And then we have P, which is prop shaft, and then we have T, which is tyre. We also have unknown vibrations, but if you just start to think about these first 3 when you start to see the data, it will really help you. And once again, we've got a short animation that shows quite nicely how these 3 are.
Yeah, so here we are with wheel balance procedure, and highly recommended is road force balancing. So you'll see this machine here, how it applies a roller to the tyre, so it actually compresses the tyre and simulates the deformation that would be on the road. There was a little animation there about placing weights about the wheel, and whilst you may have 10 gram and 5 gram in different locations, the ultimate imbalance is in one direction only. So here we have imbalanced wheel, and that is going to generate 1 disturbance for a revolution of the wheel. That's what we refer to as a first order tyre vibration. Same again, this is radial force variation. This is where we have different spring rates around the circumference of the tyre, and once again 1 disturbance per revolution. Now this must be awful to drive. This is an egg shape, so this is ovality, and if we look at that, notice how many disturbances per 1 revolution of the wheel. That is going to give us a second order, 2 disturbances for 1 revolution, which no amount of balancing is going to cure that fault. So it's worth remembering that first order vibrations, a balance may be a cure, but certainly a second and third order is not balance.
So yeah, so there's, like I said, there's a huge amount to take in when it comes to the theory NVH, and we're going to point you towards a series of videos on YouTube. So remember, our YouTube channel is PicoScope Automotive, so do go on there, do subscribe, click the like button, and the links to these videos that we're showing here and all the other things that we're going to discuss to today on today's presentation are in the description in YouTube here, so you can get to all the links straight away. So do follow those. But it really, really is worth. We don't have time, you know, in a short hour and a half presentation to really go through this in a huge amount of detail. But the 7 videos that Steve did with our good friend Frank Massey are really, really valuable. So do take some time to work your way through those. Perfect. Okay. So where can NVH help? Steve, you were going to give us some examples here.
Yeah, numerous applications. The more you use NVH, the more you'll find uses for it. We've listed just a few here. So typical complaints would be cabin noises and vibrations. Trim and body rattles, those intermittent nuisance rattles where you have to drive on a certain road surface. We've got a perfect tool within NVH called Function Generator to help you find those. That also extends to suspension noises, intermittent knocking noises, maybe rattles. With suspension, we use something called a time domain. Misfire detection, a very big diagnostic feature of NVH because there's quite a unique signature comes with a misfire. Component imbalances, of course, John's mentioned there, we have E, P and T where we have known vibrations. So as soon as you get a high amplitude at a known vibration, you've eliminated so many other components straight away. And more importantly, identified an offending component. Driveline vibrations, of course, engine transmission. And my favourite here is back-to-back testing. And this is comparing one vehicle against another. There are so many occasions where maybe when a customer is in the transition period with a new vehicle, they feel as though there is a problem with their car. Really, if we do a back-to-back test, measure their vehicle against another vehicle, we can identify characteristics, because the last thing we want to do is start trying to rectify characteristics of a vehicle. So yeah, back-to-back testing, get out of jail.
Right, great stuff. Okay, a couple of slides now just in terms of connecting to vehicle. So we're going to take our car on a road test. Are you okay to talk through this one,
Yeah, this
Steve?
is fine. This is our kit and kit content. So here we've opted for the standard kit. So you see there we've got 2 interfaces, 2 microphones, 2 accelerometers, so we can have any combination of those connected at one time. Here we've opted for a 3-axis measurement. It's mounted on the seat frame. That's generally the first road test that you carry out. Notice that the accelerometer screw thread is facing forward and it's mounted vertically as well.
Thanks, Steve, that's great. Okay, so we're going to have a quick look now at NVH kits and accessories, just so you understand what comes in the box. So as Steve said just then, we do tend to try and push people towards buying the standard kits. We've got 3 main kits here, our starter, our standard and our advanced. It's fairly straightforward to understand the difference, but the problem you will have with the starter kit is that you really are limited in the amount of measurements you can make. And as we start to run through how we connect to the vehicle and certainly how we start to try and pinpoint NVH issues, you are going to find only having one accelerometer a real restriction. So it is worth, if you can, and it does work out a little bit. It does work out better, more cost effective actually, to buy the standard kit as opposed to having the starter kit and then adding on components. And of course, if you can, the advanced kit does give you a huge amount of options when it comes to testing. So in terms of the key accessories with our NVH, so the first thing you're going to have to get your head around is the free output NVH interface. And the important thing to say on this is you can only connect into each of the interfaces either an accelerometer or a mic. So you are, for each interface that you have, you are limited to only one capture from there. We call it a free output interface because we actually do take free outputs from it into the scope. So we're using 3 channels of the scope to capture our movements. So from the accelerometer, we are capturing forwards and backwards, side to side and up and down movements on the vehicle. So just one thing I should say, the sensor extension there, generally it's used for the microphone, but you can also use it as an extension on the accelerometer if you're trying to move, particularly if you're working on a larger vehicle and you would need the accelerometer, say up to 6 meters away from where the scope's actually connected, so that's really, really useful. So we've got those two things there. We have mounting magnets for the accelerometer. Don't worry about all this too much because we're going to go through all of this practically. Steve's going to show us connecting onto vehicle as well, so we're going to go through all of the detail. And then final component within is the BNC to BNC cables. So for the starter kit, you'd only get 3 because we only have obviously 1 interface going in to the scope, but then you have 4 for the others. And we're going to explain to you how we use those 4 cables in different orders depending on the different kits you have. So it is worth having a good look through. Obviously all of the kits, all the information about NVH are on our website, so that is www.picoauto.com, so please remember that. So that's the main kits and the key accessories. So we're going to go now in terms of downloading our software. So you download our software now with PicoScope 7. And if you're not already aware, when you download our main software, so our PicoScope 7 software, you also get a bonus piece of software which we call PicoScope Diagnostics. And that is a suite of tests that really help you analyze issues with cars. Now, it started off as a battery test and an engine and a vehicle testing program, but now it's also where our NVH suite of tests live as well. So that's where you need it from. So just be aware of that. It's not in our main PicoScope 7 software. You download it, but it automatically will appear on your desktop. And it's this little icon here that you just want to keep an eye out for, and that's what you open up and start work on. And that's just a view, and you'll become very familiar with these views as we go through the presentation. That's kind of a standard view, bar graph view of a capture with NVH. So where to start? So we've got, as Steve showed there earlier, we've got our connection onto vehicle, but right at the beginning you're going to have to NVH, where to start. So once you've downloaded the software, you're going to have to activate your NVH kit, and you're going to have to pair it up to your scope as well. So you'll need an activation code from us. And Steve's going to talk us through the next few slides, and he's going to show you the detail of basically what you need to do to start working with NVH.
Thank you, John. Okay, so John mentioned there licensing. So the first time you connect your NVH kit, you will be asked to enter a license key. Now, if you haven't been given a license key with the kit, we need 2 pieces of information from you. One is the serial number of your NVH interface, and that might be TA148. It's highly unlikely to be that now. It'll be TA259. And then the serial number of your PicoScope as well. So once we have those bits of information, if you send those to support@picotech.com, we will then return a license key, enter the license key, and then your scope is unlocked forevermore for NVH. So it's the scope that you're unlocking, not the software and not your PC. So should you wish to lend your PicoScope to a colleague for NVH measurement, it will work. Okay, so let's look at the wizard and how we connect NVH. So NVH always assumes that your first measurement is to capture vibration. The first screen requires an RPM speed signal, and typically how we get that is via the diagnostic connector. So we're going to click on Diagnostics, and we're going to use the pass-through device. We typically recommend Mongoose, but any pass-through device is perfect with NVH. Deselect Elm and J1939 and leave the tick box against J2534 and click the next button. On confirmation, Mongoose here has connected to the vehicle. We see they've got the big green tick. We've got the VIN number, which has been extracted from the vehicle, and that will be assigned to the file once we've captured data. So there we have it, a successful connection via OBD. Remember, of course, ignition on or ready on. We need to communicate with the vehicle. Next in the wizard then is engine configuration. So is it inline or is it V? And then the number of cylinders. So quite a simple entry, no real technical information required there. Next one is the drivetrain arrangement. Is it front wheel drive? Is it all wheel drive, rear wheel drive, or four wheel drive? Tends to be a bit of confusion between all wheel drive and four wheel drive. Consider them both the same. So whether that's a true off-roader where the driver has control of the drivetrain, or whether it's vehicles like X-Drive or Quattro where that's managed by the intelligence system on board, still four-wheel drive, consider both those the same. Enter that and then click the next button. Next is differential ratio. This is only required if you have rear wheel drive, if you have a rear prop shaft, because if we want to calculate the frequency of the prop shaft, we need the differential ratio. Now that might be in technical literature, in brochures, in electronic parts catalogue, or technical information. It can be challenging to find for some reason, I'm not sure why. Well, I found myself in the past using Google searches to find differential ratios. Next up then is tyre size, and we've got to be quite strict how we enter tyre sizes. So it must be, in this example, 225/45 capital R 19. If you get that wrong, it will put an exclamation mark and ask you to correct the entry and show you where the entry is incorrect. NVH also supports half tyre sizes as well, so if you're working on commercial vehicle, or also inches as well. So if you're working on sort of special build vehicles where they don't have a conventional tyre size, you can enter those in that format too. Next up is your NVH interface. Well, typically we're on the 3 output interface now. That's the TA259, so we'll select that. Next will be, what do we want to connect? Well, at this stage, you don't have a choice. It assumes you're going to use an accelerometer, and that's fine because your initial road test is always an accelerometer. Connecting our accelerometer, that's X, Y, Z to A, B, C. So if you remember that, so X is blue, Y is red, and Z or Z is green. And at this point, it's an opportunity to just test the accelerometer. So if you tap the accelerometer, you'll see you'll get a response in this bar graph here. Now, mounting the accelerometer, typically where the customer is complaining of vibration. So we are making an assumption it's the driver. Best point of contact for the driver is the seat frame. You'll see here we've mounted an accelerometer on the seat frame in the vertical position with the screw thread facing forward, so that orientation will be correct. And it's a good point to add here that whilst the wizard doesn't ask you to add a microphone, I'm a firm believer that adding a microphone will give you a little bit more diagnostic information. And like John mentioned there, if you've got the standard kit, then you can do this. You can have a microphone connected simultaneously. And we'll have to go back into the menu and amend slightly for a 3-axis plus single channel measurement. But ultimately, having an accelerometer will capture all those low frequencies, and having a microphone will capture all the high frequencies. And there's also the beneficial side effect here of being able to narrate your road tests. So whilst you're in the cabin, you could be talking, it will be recorded. You could mention that you're steering left or you're braking. All that will come through in your recorded capture. And that's it. There's a summary of the basic information required. So engine configuration and cylinder count, tyre sizes, rear differential ratio. I think that's probably the challenge out of all that. And the drivetrain arrangement. Once that's entered correctly, you're ready to go for NVH. All right, I'll pass you back to John now to look at vibration setup and analysis.
Thanks, Steve. Thanks, Steve. That's great. Just the eagle-eyed amongst you might have noticed that there was a little link in there, which was a forum post around setting up your microphone. So that link, along with all the other links, as I've said, they are down here in the description on the video. So look out for those. It will just make it really easy for you to find further information. We've tried to put most of the main things we think you'll need a link to in the description below. Okay, we're going to kind of run through now the kind of basic setup. So a lot of this covers what Steve just mentioned actually, but I think it's important that we kind of perhaps go over this again and with the help of some really, really nice animations. So we're going to talk first about accelerometer positioning, which Steve has already mentioned. So here's our road test. And as Steve said, you know, we kind of assume that the first person who starts to feel or hear a vibration, is sensitive to a vibration, is going to be the driver. So we tend to use the seat support as our first measurement. And you will start to see there, so we've got our 3 bar graphs, we've kind of highlighted it there. So remember those 3 colours. Those 3 colours there respond to the 3 axes of the accelerometer. So we've got our forward and backward, our side to side, and our up and down. And the red one being the up and down, I think, isn't it?
That's correct.
Yeah, that's right.
Axis,
so,
yeah.
And that's important because in that first measurement, we know what we're trying to look for is most likely caused by an up and down movement. And that helps us then when we go on to the next part of the presentation, or the next part of the test, where we're going to introduce another measurement at a different point in the vehicle, so we can start to try and narrow down where we feel the issue is. The animation runs quite quickly as well, so you'll notice, Steve's already mentioned it, when we're positioning that accelerometer down, we want to make sure that screw thread is pointing forward, because you have to have it the same every time you set up. It's really, really important. And again, we're actually going to do this live on the vehicle in a little while, so you'll see that actually live. And I've just actually pulled out a couple of examples here. So there we are on the seat frame. We've got our 3 axes of measurement. And now what we're going to do, we're going to put a second accelerometer. We're going to put this under the bonnet, nice secure location, and then we're going to run the same test again. So let's have a look at this. So again, you know, we can have our scope in the back on the footwell of the car. We can run our accelerometer round. Like I said earlier, we do have that extension lead if you do need a little bit more. And we're positioning this in the engine bay, again making sure that we're pointing in the forward movement with the accelerometer. And now we're capturing our data. So same road test. Really important thing around road tests, different roads have different feelings. So if you're doing multiple road tests, it's really quite useful to keep all the variables to a minimal. So using and going on the same route each time will really help you when you're capturing data. So yeah, and what I didn't mention was, so on our second one, because we're generally limited to 4 channels, and I don't feel that's a problem, but we're generally limited to 4 channels, because we are looking at the up and down movement. We've just connected into the up and down movement on this accelerometer for the second measurement in the engine bay. So this is just a screenshot around what we're seeing. Anything you'd like to point out on there, Steve?
Can we expand that, John? I think, does that come up to full size? Yes, it does. Yeah. Okay, so this is positioning of a second accelerometer, measuring the vertical axis only over the right-hand front wheel. So we can clearly see that originally we captured a high vertical acceleration inside the vehicle. Putting an accelerometer outside the vehicle, now we've captured another vertical vibration, but with greater amplitude. So that's good news, we're onto it, but we mustn't jump to conclusions here. What we now need to do is start using that accelerometer like a stethoscope in effect, and we'll now try the right-hand rear, the rear left, the front left, and then logging and comparing amplitude. So here we have 34.9 milli-G. That's the level or the amplitude of vibration. In the next animation, we'll reposition and see what amplitude we get from that point on the vehicle.
There we go then. So yeah, we're taking the same accelerometer and we're moving it from the engine compartment round into the boot. And this is the carpet magnet, as Steve always likes to point out. But you're obviously going to need to make sure that it is firmly connected into the rear boot. And we're getting a higher measurement. Why do you think that is, Steve?
Well, there you are. This is how we can fall into a little bit of a trap. So clearly now our amplitude is dramatically high when we're measuring over on the rear left of the vehicle. So initially we perhaps thought we were onto something on the front right. This is why it's important to go to each corner of the vehicle. I think on the next slide, John, do we have that screen in full view?
Yeah.
Yeah, and I think we can magnify that as well when we click again. Will that come up to full screen?
Yeah, because I always think that we would expect to see that become smaller as we move away to the front, because it was actually increased at the front of the vehicle. Why do you think that is?
It was increased in the front of the vehicle, but think about where we're measuring on the vehicle. So we've now taken an accelerometer outside the cabin, which for all intents and purposes is insulated from vibration. We've now exposed the accelerometer to vibrations outside the vehicle that were originating from the rear left, but through the vehicle, through the entire vehicle components, the transfer path that John mentioned earlier, we're picking up the vibration equally at the front. Equally at the front, yes, not to the same level as we were when we were at the epicenter of the vibration. And in that animation you saw there that over the rear left we are now at 58.9 millig, far greater amplitude. We'd also gave a little tip that the DTI gauge placed on the drive shaft highlighted our out of round or our run out on the shaft, in which case it will generate 1 disturbance per revolution of the wheel. So a very easy trap to fall into, that it's a T1, but actually yes, it is T1, a component rotating at tyre frequency but not a tyre, and the amplitude is the giveaway that we are now above, or we've zoned in on the epicenter of the vibration. Okay, so this is the bare minimum setup required for the vibration measurement. So when you follow the NVH wizard, these are the components that you're going to require, and this is what it will ask you to connect. So first of all, PicoScope, of course, connected via USB cable into the laptop. And we'll now start NVH software. So we'll open the Pico Diagnostics app, which contains NVH, and we're using the early access version here. Click on NVH, and it's start a new test. So we see here the first thing it's asking us for is how are we going to get RPM value, and we're going to use J2534. Now that's where your Mongoose lead is required. The Mongoose lead will connect into the diagnostic connector, and of course USB then into the laptop. Now we have one already in the diagnostic connector, as you can see here. We'll bring this around and then connect this into USB. There we are. Next, we have the ignition on. So just ignition on at this stage, and click next. Now Mongoose is going to connect to the PC first of all, so it recognises Mongoose. Vehicle is connected, there's the green tick, and there is the VIN number as well. So next up is configuration. So it's an inline 4-cylinder. These are already populated for us, which is good news. Previous vehicle using this software must have had similar settings. Now it's the drivetrain arrangement. Now this is an X-drive, so we go for all-wheel drive. Rear differential ratio, luckily I happen to know that this is 2.81, so we can proceed. Tyre size is 225/45 on this vehicle, 45 are 19s, and we have got different size tyres on the rear of this vehicle. So this has 255/35 capital R19. Notice there the exclamation mark if your entry is incorrect. It's a 3-axis interface, and that's exactly what we've got here. 3-axis interface, and we're going to connect an accelerometer. So we follow this through, connect the accelerometer in channels A, B and C. So first things first, accelerometer into the interface, and note the red LED is flashing there, so we know that the battery inside here is good. Notice X, Y, Z goes to A, B, C. So there are our axes. Okay. Notice also in the software that whilst I'm tapping the accelerometer, we get an instant response from the bar graph there. Now it says attach the accelerometer to the seat frame. Remember, this is important. It's the screw thread facing forward and in a vertical orientation. Click next, and we're actually finished at that point. We're ready to go. So we could press start recording, but there's a point here where I'd like you to go back and consider something else. So we click on the setup tab, and I'd like you to change the settings to 3-axis plus single channel. Also in here, note that we have our configuration for the 3-axis measurement. It's passenger compartment. It's important to add notes as to where your accelerometer is located. So on this vehicle, it is the passenger front seat inner bolt. Now, the next one is another interface. We're going to add the TA259, so a second interface unit, and we're going to add a microphone. So this is where the standard kit really comes into its own, because you'll be able to add a microphone and accelerometer and measure both vibration and sound simultaneously, and that will connect to channel D. We need to inform the software that we've got a microphone connected. So there we have a microphone, and the microphone is going to be inside the passenger compartment, so we'll leave those settings as is, and we'll just add in here rear view mirror and click close. Now our microphone connection is the same as the accelerometer, and it's the same confirmation as well. We need to make sure that the red LED is flashing, so we know that the battery is good. Hopefully we can see that there. And routing these cables away from any vehicle controls, we'll mount the microphone up at the rear view mirror, or wherever the driver happens to complain of the noise. So in this scenario, we use a gear tie, and then we simply wrap the gear tie around the microphone, and there we have it. That's absolutely perfect now. The settings are correct. We have a microphone inside the cabin to capture all the audio, and we have an accelerometer on the seat frame to capture all the vibration. All that's left to do now is record and analyze, and click on start recording. Alright, so we're now going to describe a new setup that's using the accelerometer as a contact microphone. So it's a little bit of a cheat, in fact. We go into the software and we say we've connected a TA259, but we claim that the accelerometer that we fitted is in fact a microphone. It only requires one input, so it's channel B only. We're already connected to the OBD via our breakout box, so we're using the CAN breakout box so that we can plug in Mongoose and obtain engine speed and road speed. In the software we are connected. You can see here it's Mongoose is connected and it's written in green. We're not too concerned about vehicle information beyond engine, so we've got an inline 4-cylinder, and that's really all the information we want, and you'll see why as we go on. So we'll start recording, and just notice what happens when I tap the accelerometer. We can see in the signal history we get an instant response. What we're going to do now, we're going to start the engine, and we're going to place the accelerometer on different components. So I'm not too worried about orientation, because we're going to imagine that this is a stethoscope in effect, and it's just purely a contact microphone. So we'll try vibration levels here and audio levels on this bracket here. We'll move across to, let's say, the strut, and we'll just compare levels of vibration and noise from the engine to the chassis. We'll then place it on the alternator, have a listen there, and then place it finally down here on the air conditioning compressor, and then see, we'll compare all of them with one another. So at this point now, we need to start the vehicle. So it's just idle speed at this point, and we'll start with accelerometer on an injection pipe, and we can see the events there in the signal history. I'm just going to auto scale. We'll take that off there. We'll on the engine. I've tapped it deliberately so we can see the transition. We'll then come on to the chassis where there's virtually no vibration, no audio. We'll now go down onto the alternator, and I'm holding it on the alternator because it's aluminium. I'll take it off there and I'll reach down and get onto the air conditioning pipe. And we'll finally take that off. We'll pause the software, which we can do with the space bar. And then switch off engine. So because we've actually connected the accelerometer as a microphone, we can now play back this audio. So if I press the play button now, we should be able to hear, there we are, there's our injector pulsations. Notice the amplitude as well by comparison. Next was on the engine lifting bracket, so that's general engine noise. Then we came off there and there was virtually nothing in the chassis. Of course there will be vibrations, but audio-wise virtually nothing. Next was alternator, that was just purely holding it on the body of the alternator. And then finally, air conditioning pipe work. And of course, we can analyse the frequencies within. So if I was interested in, let's say, injector pulses, I'd be looking at the harmonics. If I was interested in generator, I'd be looking at the harmonics there. All right, I hope that helps.
Okay, so we're going to have a look at NVH noise capture and analysis, and Steve's going to take us through a little case study that he did a while ago, and it just really explains just how important the use of the microphone can be when looking at issues around sound.
Yeah, thank you,
There
John.
Steve.
So yeah, as John mentioned, those frequencies above 200 hertz, that's where the higher frequencies, that's where we want to use the microphone. Equally, they will capture frequencies low down as well, so you get quite a bang for your buck here. We're going to put a microphone inside the cabin off the rear view mirror. If it is that the driver is complaining of a noise by his right here, or he can hear it there, it may be from the door, then let's place the microphone in that vicinity, because microphone placement is essential. So here is our connection. We're going to utilise channel D. Why not? It's a spare channel, so we'll keep our 3-axis measurement and a microphone, as we'll demonstrate later on. Yeah, so there is our connection. Here is our microphone. Remember, it is a microphone, it captures all noises. And here is one of those frequencies that is not linked to engine speed in any way. It's an electric fan. So it's going to be an unknown vibration because we won't have any link to the frequency of that component. So notice there we've got periods of high acceleration, high vibration and high noise level, which is captured by the microphone. Periodically, because remember the cooling fan cuts in intermittently, it's not in all the time. And again, we'll see that as an unknown vibration. Here it is. I've moved the marker here to concentrate on the vibrations and noises just in this zone here. So we see where the amplitude is at its greatest. And then here we can see unknown, the yellow peak in particular, 39.2 hertz. Now that is a cooling fan speed, cooling fan frequency. And how can we identify that? Well, we've got a video that we've done from the archive. I think it's on our next slide here, yes. Episode 6 of the session that we did with Frank, we did a practical exercise where we'd introduced a deliberate imbalance. You saw in the earlier video how it was actually a broken fan blade. In our example, we just placed a bolt on a fan blade. We've got this huge imbalance, so when the fans cut in at top speed, we've got this noise and vibration generated in the cabin, equally detected by both microphone and accelerometer. But if the microphone is the only sensor you've got in the cabin, well, so be it, you will capture that, but it will be an unknown frequency. So up until this point, we've looked at vibration only. What about noise? What about complaints of noise, cabin whine, whistle? These are all higher frequencies. We've got a case study here that we can replicate. That is what turned out to be a cooling fan issue. But the story goes that minor accident damage, front end of a vehicle. Body repair is perfectly fine, but at certain moments there is quite an intense vibration passing through into the cabin. So this is where, if it's a complaint of noise, then we should include the microphone. We can still use the accelerometer, but let's add the microphone and place that in the cabin, ideally next to the driver's ear if it is them who is complaining of the noise, or maybe rear view mirror, because that will give us an overview of all the noises present in the cabin during the road test. So let's have a look at this animation. So here then we're adding the microphone to channel D. There we have the issue. This was damaged cooling fan, and here we're displaying the noise in bar graph view. So you can see there we've got the vibration, the intense vibration that comes on when the cooling fan comes on at top speed, and we're displaying there the bar graph view. On the right hand side you'll see the top 5 unknown vibrations, and that's unknown because it's not linked to engine or road speed. It's an electric cooling fan.
So what I've picked up there from the bar graph, Steve, is that it is an unknown frequency. It's not related to anything that we're able to synchronise from known data from the vehicle setup.
Yeah, that's exactly right, Frank. And the view we've chose there, on the right-hand side, the bar graph view, is showing the top 5 unknown vibrations. We've highlighted vibration 1, 39 hertz it is, peak vibration detected by the accelerometer in the vertical axis, but also detected by the microphone inside the cabin. So I think we're certainly tuned into the customer's complaint. Let's go and replicate this on our van. So what we've done here with the van is simulated exactly what you saw in the animation. We've introduced a deliberate imbalance to the cooling fan. We've also then introduced the microphone into the cabin. So not only will we measure the vibration, but we'll measure the sound, which, remember, is one in the same thing. The microphone and the accelerometer both detect the vibration, the sound generated, and display them differently but at the same frequency. So we can use either or in this scenario. Certainly this would be your choice of measurement for chasing a transmission whine, for example, or brake squeal, anything sort of above 200 hertz.
So really this technique is for indiscriminate noises which really can't be easily identified to a particular component.
Yep. Okay. So connection-wise, we've gone for 3-axis plus single channel. So still use one accelerometer measuring all 3 axes. But the additional channel now, channel D, is the microphone connected to the rear view mirror. So in a road test example, the microphone will detect all noises, but there's a specific noise we're chasing here, which is the noise generated from the imbalance in the cooling fan.
And I guess from this setup, would you also recommend moving the position of the microphone once you're honing in on the noise to perhaps increase the amplitude of the results?
Yeah, the opportunities are endless really, because certainly always keep a microphone in the cabin as a reference, because that's what the customer can hear. Perhaps keep one in the cabin, one in the engine bay, and also keep the accelerometer as well, so you've got 3 points of reference really. Think of bearing noise if you've got the luxury of 4 microphones, 4 accelerometers, 1 road test, 1 measurement with a reference inside the cabin.
Would you also recommend multiple microphones in the same way you would accelerometers?
I would, most certainly, yeah. The advantage really of the accelerometers is we lose a lot of the ambient noise. However, the microphone gives a real, true representation of what the customer can hear. Mm-hmm. So always include a microphone in these kind of measurements as your customer reference, as a kind of an indication, a representation of what the customer can hear. So the setup here for the cooling fan noise vibration, we've gone for a static RPM. Remember, we're not road testing, we're not looking for a vibration relative to engine or road speed. We've gone for a 3-axis plus single channel measurement. 3-axis is our accelerometer mounted to the driver's seat, and the microphone is up at the rear view mirror. That's giving us the customer's audio reference, if you like, what the customer can hear. So if we go to record and analyze, we'll restart the recording because we've got previous data here. There's a warning there to let you know that if you do restart the recording, anything you have here is now lost. We'll start the recording here. We'll use the auto scale feature, and we'll let the software the scan tool software run the cooling fan. Okay, if we can stop the cooling fan there, we'll pause the software, and we can then drag our highlighter here, pull that onto the offending area, which is this area here. Use the right-click auto-scale feature, and we can see that both the accelerometer and the microphone have picked up the frequency, the offending vibration noise that the customer can hear. We can just use the channel in view and concentrate on the audio. So channel in view enables us to take away channels A, B and C, which is our accelerometer. And we're left then with this offending frequency, the highest peak in the spectrum. This is approximately 38 hertz, 36 hertz. This is our offending frequency. So
now how can we, Steve, we've got this 38 hertz,
yeah.
How can we then relate that to a specific component?
Right, it's a great question. I mean, we know that that is the peak that we've captured during the vibration, during the noise. We know that frequency and speed are directly related. Hertz times 60 is RPM. Well, we could actually use the speed of the cooling fan, because if we've got one disturbance from this cooling fan, remember in the animation there's a blade missing. On this cooling fan we've added weight. One disturbance per revolution. Let's use an optical pickup on the fan, which theoretically should give us a frequency of about 36, 38 hertz.
So just using an independent, handheld, optical
pickup.
RPM interface.
Yeah,
okay.
Using PicoScope.
Right.
So how have we created the imbalance in the cooling fan here? Well, simulating what you saw in the animation, a missing blade, we've placed a bolt through this blade here. So for one revolution of the fan, that will create one disturbance. How can we determine the speed frequency of this fan? Remember, speed and frequency, one in the same. We attach some silver tape here and point the optical pickup at the cooling fan. So every time the optical tape passes the optical pickup, it generates one pulse per revolution. That will give us the frequency of the fan. We can then use PicoScope to not only count those pulses but display the frequency of those pulses, which should come out around about 36 hertz, because that's what we captured our vibration, our peak amplitude vibration at 36 hertz in NVH. So using the optical pickup to determine the frequency of the cooling fan, we'll connect that into channel A of PicoScope, run the cooling fan at the top speed, there is only one speed setting for this one, and see what PicoScope displays in terms of frequency. As you'll see there, I've actually placed a marker signal ruler at 36 hertz, so PicoScope is frequency coupled. And theoretically, if we've got our maths right, when we run the cooling fan, we'll see that top speed or peak vibration occurs at 36 hertz. Could you run that, please? Okay, we switch the cooling fan off now. If we just pause the software at that point, we can see how the frequency climbed as the speed of the fan increased and topped out approximately 36 hertz. If we do the maths on that, 36 times by 60, the cooling fan 2,160 RPM. So another way, Frank, of qualifying the frequency speed of a component.
Sure. It may be worth mentioning also that your channel input command has been set not from AC, DC, but to frequency to obtain this information.
Yeah, the frequency coupling of PicoScope, so that's available in the current 4000 and previous 4000 generation of PicoScope.
I think the really interesting thing I've picked up from this bar graph is that we can clearly see on the right-hand side that this frequency of around 35 Hertz sits quite nicely between E1, E2, so we know it's not the engine. And I think the way I'm thinking at the moment is, if we increase the frequency of the engine, there could be a situation where we get resonance, where we get two forces out of balance which add together. But looking at it in this way, we're able to separate this issue and see very clearly that this is a non-engine related component causing this problem.
So we had concentrated on the frequency view. This is exactly the same data, no different, but in bar graph view, where we've used the software to highlight the known vibrations on the left and the top 5 unknown on the right. In this scenario we had 39 Hertz. Remember, cooling fan frequency would be dependent on battery voltage as well. So if we are going to run the cooling fan for simulation, battery voltage is key for RPM. So that concludes the introduction of microphone in this presentation. Join us in the final presentation where we'll look at a number of real-life case studies where we've used a combination of the accelerometer and the microphone to determine the cause of customer complaints of vibration and noise. I hope you found that interesting, an example of typically where the microphone comes into its own. Remember, if it's the only sensor you've got, then please place the microphone inside the cabin. Right, so moving on to case studies then. So these are real world examples where NVH has saved the day. Here is a classic. This is a T3 vibration. So we've talked about T1 first order vibrations, tyre vibrations. What is T3? Well, that's 3 disturbances for every 1 revolution of the tyre. And focus here in the graph view and notice how this vehicle is accelerating. The customer complaint here is that under acceleration only there is an awful vibration in the cabin. Take your foot off the gas pedal, the vibration has cleared. Well, clearly we can see a T3 vibration, 3 disturbances again for 1 revolution of the wheel and the tyre. But green in the lateral, so it's affecting the car left and right. So what typically can give us this scenario? Well, in the next slide we'll reveal this is a tripod joint of a drive shaft, and hopefully you can see that here we have a bright spot about 3 points around the tripod joint. So under full load we're getting movement of the shaft and misalignment of the shaft such that it generates 3 disturbances per revolution. All right, next up is wheel bearings, NVH in the real world, looking at bearing diagnosis, not just wheel bearing, but this is a classic example of a bearing. I just want you to notice the harmonics here, multiple spikes. Channel A and channel D are connected to the same component. They're actually one accelerometer connected as an accelerometer and then also connected as a microphone. This is a way in which we can cheat slightly and listen to our accelerometer as a contact mic. So how on earth do we use those multiple harmonics? There's no one single frequency associated with a bearing when you get the degree of wear that you're about to see on the next slide. If you can imagine a tin can connected to the back of your vehicle being dragged along the road, the amount of deformation and clattering noises that it would make, there'd be no uniformity to it, it would just be sporadic, and these are the type of harmonics that you will see. So we can clearly see that there's something wrong there on the left-hand front bearing, because that's where those sensors were connected. And just look at these bearing races and the rollers and the contamination within that bearing. It's an exceptional example, but what I want you to understand is bearings generate multiple harmonics. Okay, so T1 in the real world. This one is incredibly powerful when it comes to looking at engine diagnosis. But be aware of something that can trip you up, and that is, at first glance, this peak here appears to be a T1 vibration. But in fact, if it is at 44 miles an hour when under load. If you're 44 miles an hour when you're not under load, then this comes down. So it's kind of counterintuitive as to what it could be. So we'll add an additional marker, what we call E0.5. This is one disturbance for every 2 revolutions of the engine, which at this road speed happens to equate to the same frequency as the tyre. So it could have been very easy to mistake. E0.5 is the typical vibration order associated with misfire. So you were under load, remember? Engine is misfiring. One disturbance every 2 revolutions of the engine generates an E0.5. Very powerful tool to confirm that you have a misfire, which may not be immediately apparent from all the tests that you can do in the workshop. This is something that you can do non-intrusively and under load. Okay, and the final one is using a microphone again. So this is a whine from a transmission. And just note here that in the signal history, this is a hybrid vehicle and the engine is not running. So these are fending frequencies. This one in particular at 1 kilohertz is present without the engine on. So already we've eliminated engine from the equation. So the transmission and the vehicle is being driven by the motor. There is an offending 1 kilohertz vibration, 1 kilohertz high frequency noise that's been detected by the microphone. And there's a pointer I want you to notice here at T1. That is the frequency of our tyre. Why would that be important? Well, let's have a look. So here we have our wheels rotating at a frequency of 5 hertz, which means this crown wheel is rotating at the same frequency. Now, using maths here, we can calculate the frequency of the counter gear that goes between the motor wheel, motor gear, counter gear, and crown wheel. So once we know the frequency of this gear here, based on this ratio, we know the tooth count for this gear, the tooth count for this gear, and the meshing frequency with the power split device from the management here, at that speed generates a frequency of 1 kilohertz. So we're able to diagnose particular offending components within a transmission without dismantling the transmission. And that's very powerful for support teams and engineers alike, because they will know the frequencies of these gears. They will also know the tooth count, so they'll know the tooth frequency. So again, great information that we can present to engineers and technical support staff that supports the customer complaint and aids with diagnosis. And in this scenario, the transmission was replaced and the noise level, while still present, had been reduced dramatically. The final one is rattle finder. This is a very simple test we do with a function generator. In this scenario, I don't think you can see here, this nut is not clamping the washer to the chassis. So the nut is able, the washer is able to float between the nut and the chassis, which generates a rattle noise, but only under certain road conditions. Now, to try and generate that may be multiple road tests, and sometimes you may not get success initially. Well, with the function generator, we vibrate the cabin using the in-car entertainment system. We can tune in a low frequency, generate the buzzing or the rattling noise, and then walk around the vehicle looking for, using our senses, no more than our senses, to locate where the rattle originates from. Once we got this rattling, it did not take long to find that the washer was clamped. It was the nut with integrated washer was clamped on the frame and not clamping on the washer. A new nut, you can see the witness marks that have been left there. We've got good clamping force now. Rattle is cured. So on the subject of rattles, we have a video already on YouTube, Rattle Finder, and we run through this whole test procedure and how we link NVH, our laptop, to the in-car audio system and generate those frequencies that can generate rattles. Following on from our previous video looking at cabin noise, we wanted to do an update to show you how we tackle this issue. I think one of the worst job cards to receive on a Monday morning is something like investigate intermittent cabin rattle. Vehicle has been in 2 or 3 times. Where do you start? How do you approach this subject? Often it's countless road tests and there may be no conclusion. So How we approach it, we use the Pico NVH and we use the function generator feature, and we'll describe the whole procedure as we move on. So here's the car with a customer complaint of a rattle in the cabin over uneven road surfaces. And connection wise, we need an NVH license scope, so you will need an NVH kit to acquire the license. Connect that via USB to your laptop, and then the audio out from the laptop we're going to connect to the audio in, or the aux in, on the vehicle. So any sound that is generated from the NVH software is going to pass through the cable into the in-car entertainment system, where we can control the volume and drive the speakers at any frequency. So now the connections are handled, we now move on to opening the software. Remember, you need a licensed Automotive PicoScope connected. We click on NVH, that will open the NVH wizard, cancel the wizard, and we go to the options, and it's function generator. Now the function generator will only work with a licensed Automotive PicoScope connected to NVH. So here we are, here is the function generator, and we can dial in any frequency we want. We can use the scroll bar, or we can enter a value. But we want to do something called sweep, and we want to start at 0, and because it's vibration, it's very low frequency, we want to stop at 100 Hertz. And we'll do that over a 30-second sweep. And we've got this audio now playing into the vehicle. We've got, in our media settings, we go to external devices and we click on the aux. That's the aux gain control. That's set to just over half on the vehicle, and the volume on the vehicle, on the laptop, sorry, is set to around 80. So let's have a listen. So we'll switch this off. Sorry, we'll switch the audio on, so we'll remove the marker. And then we'll sweep up. You see the frequencies coming up there. This is very low at the moment, so we can't hear anything. We can start to hear it now. I'm going to hover over the pause button because I want to capture the point where I can hear the rattle. So there, definitely a rattle at 69 Hertz, 68, 67. 66 it's going at 65, so we can go back up. There it is, 67 Hertz approximately. So there's one, and we'll resume. Oh, there's one, 97, 67, 97. So now pressing on trims to see if we can find a rattle, but you'll find that sometimes rattles that can be heard in the cabin are actually from outside the vehicle. And there we are. And that happens to be the side skirt on the vehicle. I'm just pressing the side skirt and that noise has gone. Let's take that down to, I think it was 67. There we are again. It's a lower frequency but still responding. Yeah, pressing on the side skirt stops the rattle. Alright, I hope that helps. So there you have it. I hope you'll agree that's a fairly non-intrusive test using the function generator of NVH. Low frequencies work best. We're trying to make the cabin vibrate, so if the vehicle is equipped with a subwoofer, then all the better. The real beauty here is that no road testing was required. Can you imagine trying to generate that rattle on the road? You'd got to drive the vehicle at a certain speed on a certain road surface. With this function generator we can sweep across the entire spectrum and home in on a particular frequency until we get the component responding to the vibration. Final word is that customer is always king, and it may be worth you doing a frequency sweep with the customer in the cabin so they can point out the rattle of interest. Be careful though, you're going to reveal rattles they weren't aware were present in the car. And as ever, the proof is in the pudding. I want to take you through a case study from Randy Jansen in the US, who's been looking at a Corvette with a rattle, using this technique to diagnose and rectify the concern. Once again, thanks to Randy Jansen in the US for looking at this and sharing this. This is a Corvette with a suspension noise. So, customer complaint, irritating noise in the suspension. Technician had watched the Pico NVH video, so the previous one that we created on this noise, how to use the function generator. Using this approach, managed to pinpoint the fault, and more importantly, the vehicle is tested while stationary. A true valid point, that one, is that there's no longer this repeat road testing. So there's the setup. That's straightforward, as we've demonstrated. It's use the aux input. Remember, if you've got Bluetooth, then you could perhaps Bluetooth the audio that way. That keeps your laptop on the outside of the vehicle and stops you having to trail wires inside the cabin. Right, here is the fault. What do you see here? Okay, no prizes for guessing that. Okay, flange nut, eccentric washer there. Looking a bit closely here, notice the flange on the nut is not actually bedded down onto the washer. So the nut is tight, but it's actually tight on the frame, right there. The washer then is allowed to vibrate because it is not tight, and using the function generator, we're able to make this washer vibrate, and then once we've got the responding frequency, we can go around and search for where the rattle is coming from. So the fix is to remove the nut, replace it with the correct nut. I think this is great here. Look at that, the witness mark in the chassis. Same again there. Obviously the correct nut has been installed. Look how the thread has changed as well. How many turns we are down on the thread. And the witness mark that's been left in the chassis there as well. Okay, so it had rear leaf springs installed and the incorrect nut had been used. Okay, the nut had tightened on the cross member instead of the eccentric bushing. Witness marks, they clearly demonstrate the fault condition, and the correct nut repaired the vehicle. Thank you once again, Randy Jansen, for taking the time out to help others. Let's just go back one slide. Can you imagine trying to find that with a road test? Challenging for certain. I hope that helps. Take care. Okay, I hope you found that interesting. I'll pass you back to John now, who can complete the presentation.
Thanks, Steve. Okay, so just to kind of tidy things up now, hope you found this presentation interesting. We've tried to pop in here some essential links, so you've got a route into for further information. As we've said, you know, trying to do justice to such a big subject in a short space of time is difficult, but we have had a lot of requests for a shorter kind of intro to NVH, so hopefully we've covered enough to whet your appetite for it. Like we've said, really important. We've got nearly 3 hours of video that Steve did alongside Frank Massey, which takes you through all of the theory and then practically how you use NVH to find real world problems in the workshops. There's some really good stuff in there, and we go into a huge amount of detail actually, so please check all of those videos out, and as I've said already, make sure you subscribe to our YouTube channel. By having more subscribers, it means that we'll do more and more content and bring you more and more information about working with PicoScope. One thing we haven't mentioned, but it is worth, if you haven't already, please do download our app. You can download it on any smartphone or tablet device, and it's a really good way of getting information. It's more around working on the electronic side of PicoScope, blah, 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 blah. If you haven't already, please do download our PicoScope app. You can download that for any device, be that a smartphone or a tablet. And we take you through there what we call the diagnostic journey. So that really is useful for particularly beginners, but we do start to touch within the app on NVH issues. So if you haven't already, please do download that. Okay, and remember our videos, so we've kind of done YouTube, but also our forum. There's a huge amount of information on our forum, and if you remember on some of the earlier slides, Steve had put some links to specific forum contacts looking at NVH, but also specifically around tests set up for different tests. So well worth looking out there and becoming a member on the forum as well, so you can set up your own username and password. And a reminder that is the same username and password that you will need for our waveform library. when you start to diagnose problems. And there's a list of essential links. We've also put them in the description below. And I've also there just popped a picture of our website. So just a reminder, our website is www.picoauto.com, but all the links are indeed in the description below. So that's it for Pico Planet. And we'll just finish up with our final thoughts around PicoScope NVH. Thanks guys, thanks for joining us on this introduction to NVH. We hope you found that interesting and informative. Like we said at the beginning, it is supposed to be quite basic, but all the links down there for further information. Just one huge thanks to me for Steve for all of his technical input today, really amazing. So that's it from us. Anything else to say, Steve?
Not really, I just hope you found the practicals really useful. The wizard in NVH is really helpful. It will guide you through to that initial setup, and that's what's important.
Great, well, thanks for joining us, and we'll see you again soon on Pico Academy.